Universal Chiplet Interconnect Express, UCIe. Let's try to unlock the raw potential of UCIe interconnect in this session. The electrical layer forms the foundation for this revolutionary chiplet communication standard, enabling high-speed, low-latency data exchange between two dies. In this session, we will try to deep dive into the electrical specifications that governs this critical layer. The UCIe specification document published by UCIe consortium as the following main titles in the document: introduction, protocol layer, die-to-die adapter, or logical physical layer, electrical layer, sideband, configuration parameters, interface definitions, and compliance. So in this session, we will be focusing on the fifth topic, the electrical layer, because that's what we are concerned about our the circuit level designs. Now let's look into some key attributes of electrical specification. This specification supports the data rates for 4, 8, 12, 16, 24 and 32 giga transfers per second. And this specification support for advanced as well as standard package interconnects. This specification supports provides support for clock and power gating mechanisms. As we know, the clock and power gating mechanisms, a couple of mechanisms, for reducing the power consumption. Single-ended unidirectional data signaling. Instead of differential signaling, it mandates single-ended unidirectional data signaling. It also mentions DC coupled point-to-point interconnect, and it supports forwarded clock for transmit jitter tracking. In UCIe, the transmitter doesn't just send the data; it also sends a synchronized copy of its internal clock signal called the forward clock along with the data. Okay, the transmit jitter tracking, the receiver circuit in UCIe utilizes the forwarded clock to track the timing variations like jitter introduced by the transmitter. Matched length interconnect design within a model. The interconnects needs to be matched because at high frequency, even a small some femtofarads of cap also introduces a big change in delay between the two consecutive lines, right? Matched length interconnect design. And driver strength control and unterminated receiver for advanced package. Traditionally, data receivers, have termination resistors placed at the end of the interconnect to absorb reflections and ensure proper signal levels. In some advanced packages, right, the receiver might not have a termination resistors. So UCIe, mentions unterminated receiver for advanced package. And it also talks about driver strength control. The way we can understand is maybe how much current it can pump out. That is the one way to do it, or what is the voltage, signaling levels. The transmitter, termination and data rate and channel reach dependent RX termination for standard package. This is the specification talks about. Let's look into one more concept, interoperability, because that's very much important here. Because these chiplets can be manufactured by different vendors, different foundries, different technology nodes, right? Interoperability is an important part. In that, let's look into first topic, data rates. This is a clocking architecture. Left is the die 1, right side is the die 2, and we have got the couple of signals going from die 1 to die 2, So what is the mandatory support? So 4 giga transfers per second, that's the minimum data rate mandated by this protocol. Okay, 4 giga and all the rates between 4 giga transfers per second and the highest supported data rate by the device. For example, look at it. For example, assume your device supports 16 giga transfers per second. Okay, and this device not only should support 16 giga transfers, but also should support 4 giga transfers per second, 8 and 12 giga transfers per second. This is a mandated data rate to be supported. Okay, so for signal integrity purposes, one can use spread spectrum clocking is allowed. Okay, but there is a catch point here. The 0 ppm difference between local transmitter and a remote receiver. This is something one needs to be taken care if we are going to use spread spectrum clocking. Now let's get some overview of this interface. We can you see it has got it supports advanced package model as well as standard package model, right? Let's look into the advanced package model first. That is this is a block diagram for X64 and X32 advanced package model. It uses advanced packaging technology. This one, embedded multi-die interconnection bridge or chip on wafer on substrate. These are some of the advanced packaging technologies, and it features like for example 64 or 32 data lines. Okay, the signaling the UCIe mandates the single-ended signaling, so reference to the ground. Okay, but the data lines, if you look at it, right, it is either 64 or 32 data lines. And it also has a track lane, low speed sideband for control, like initialization, training and configuration, right? So these are some of the features. In addition to advanced package module, we also UCIe also mentions the standard package module. This is a block diagram here, right? So what is the difference between this and this is, right? This package module uses traditional standard packaging with larger pitch. The features are 16 data lines compared to the 32 or 64 from advanced package model. It is 16 data lines. Of course, signaling remains single-ended only. As similar to the advanced package model, it also has a data valid lane and track lane and low speed sideband for control. Control means initialization, training and configuration, etc. In addition, we have an optional multi-module aggregation. For example, multiple modules, 2 or 4 can be aggregated to deliver additional bandwidth. One more reliability, consideration here is, the UCIe, the standard specification recommends recommends to limit VOH to 100 millivolts above receiver's power supply. For example, this generally think like this. This is my signal. This is my VOH, and this is my, assume it is a VOL. Assume this is my reference voltage. So receiver power supply voltage, right? This is one. I don't want this signal to go by say 100 millivolts above it. This is the reliability consideration. Now either it can damage or it might create stress on the related nearby the devices. So and a circuit guy can can build a worst case protection circuitry for to limit this VOH value below 100 millivolts of power supply, receiver power supply. Now let's look into this electrical summary. Okay, some of the parameters are given here for both advanced package module as well as standard package module. Okay, and this is for different data rates also mentioned here. Okay, for example, data width per module, it means it's a number of bits that can be transferred simultaneously in a single module. It means parallel. Okay, so wider data paths move more data at once. Okay, so it means 64 data width is equal to 64 means there are 64 parallel, I can transmit the 64 bits in parallel at the same time. Okay, and what about data rate then? Giga transfers per second. The speed at which data is transmitted, measured in giga transfers per second. Okay, higher data rate means faster transmission naturally. So then the third one, right, the power efficiency, we can say that picojoules per bit, you can say that, right? So it's a targeted energy consumption per bit transferred, measured in picojoules per bit. Okay, lower value indicates better efficiency. Okay, next the fourth one is the latency target. Okay, so the maximum allowed delay between sending and receiving the data. It's also measured in unit intervals. Lower latency means faster response. Latency means simple and delay, that's all. Okay, it's all together, takes plus rx together. Okay, then what is this next one, right? The idle exit or entry latency. Okay, so maximum delay to enter or exit the idle power state. Like sometimes your device can go to the idle state, right? So what is the the maximum delay time it takes to enter the idle state or exit the idle power state. Of course, unit is nanoseconds. So low latency naturally you preferred. Okay, so what is idle power then, right? The percentage of maximum power consumed when the module is idle. Okay, so lower percentage indicates better power saving in idle states. Then channel reach. Okay, what is this channel reach? So the maximum distance a signal can travel through the channel, okay, before needing to be retransmitted. Okay, so next one is a die-edge bandwidth density. Okay, so data transfer rate per unit area along the edge of the chip, measured in gigabytes per second per square millimeter. Higher density signifies more efficient use of chip space for data transfer. Simple, data transfer rate per unit area. Okay, bandwidth area density. Okay, overall data transfer rate per unit area of the chip. Okay, measured in gigabytes per second per square millimeter, similar to the die-edge bandwidth density, but considers the entire chip area. Okay, so what is 5-dimension width then? It's the physical size of the PHY interface. Okay, measured in cubic micrometers. Okay, smaller, of course, smaller size can be desirable for the space constrained applications. Then what is the depth, 5-dimension depth? It's a similar concept, right? Okay, it's a physical size of the PHY interface measured in cubic micrometers. Then EST, the last one, right? So it refers to the the electrostatic discharge standard, indicating that what kind of a level of the electrostatic protection the module is required or it offers. Okay, so because it's a chiplets we are talking about, right? It is not really exposed to the real humans, the human handling, right? Ideally, see, we are not talking about HBM protections. And those people are talking about 500 volt CDMs for 2000 HBM. I'm not talking about that. CDMs, when it comes to CDMs, we talk, those chips talk about 500 250, sometimes bigger also, the 250 volt or 500 volt CDMs, right? Here, because it is inter package, we are talking about 30 volt the CDM production. Okay, and we are anticipating that this will the mandating the expectation, like the is going to 5 or 10 volts in future. Okay, electrical specifications, right? Let's get into some circuit level or block level. Let's look into transmitter now. Okay, so this is the TXT mentioned. So this is what we are talking about. Okay, we have transmitter data, transmitter clock, this also data, transmitter data. Okay, so we transmit mainly 4 signals from my transmitter side. there are data, of course, data, valid, clock, and track. Okay, track. So what is data then? Data is a workhorse. It means the carrying the, it is a real actual information, carrying the actual information between the chiplets. Each data lane is transmits a single stream of bits. For example, if we have got 64 data lane, it means we need to have a 64 transmitters are driver lines. Okay, so data is that. So then we also have a valid, the signals and along, sent along with the data. Okay, so it's like a traffic light for the data lines. It tells the receiver if the data is valid information or not. It's all about, the part of the protocol encoding and sending it out. Okay, of course, it enabling features like power saving during idle periods and proper data framing. It's all part of these are part of it. And we all see, we forward the clock also, right? So the clock signal, the conductor of the data orchestra, I can say that. Okay, the signal provides a timing reference for the data transmission, ensuring both transmitter and receiver are in sync for accurate data transfer. Okay, and remaining is the fourth type of signal we send out, is track. It's an adjuster helping the receiver compensate the environmental variations. Okay, so this signal allows the transmitter to send specific clock pattern, for example 101 some number, okay, clock pattern upon request. By analyzing this pattern, the receiver can fine tune its timing and improve data reception accuracy. Right, so now we understood what are the four. We send out four kinds of signals from the transmitter to the receiver side of the chiplet, right? Other chiplet. So let's see what are these data lines then. Data lines are each module, for example, each chiplet, let's call it as, okay, each module has n single-ended data transfers. For example, the advanced package module may be having 64 data lanes or 32 data lanes, whereas standard package module can have 16 data lanes, right? It means 16 data transmitters are there. So this n, it means number of data transmitters, varies based on the module type. For example, x64 advanced package, it has got n is equal to 68. It means 64 data plus 4 redundant. Okay, whereas x32 advanced package module will have 634 single-ended data transmitters. That includes it, that means 32 for data and 2 are redundant data transmitters. So we have got a standard package module that has got the 16 single-ended data transmitters. So data lines we understood. Okay, so we can also have additional transmitters. For example, for clock, a pair of clock transmitters for synchronization. Right here it is. Okay, and at the same time, track signal transmitter for error correction. Okay, so this is a track, and these are clock, a pair, and we have got a data. For example, it is 68 and valid 4. Okay, so valid signal we understood now, right? So what is the meaning of valid signal? It gates clock distribution for fast idle mode entry exit, used for data framing, implemented similar to regular data. Okay, this I think we got a pretty much picture of a transmitter topology. Now let's look into the driver part of the transmitter. UCIe mentions transmitters to be optimized for simplicity and low power operation, natural expectation. Okay, so this is an example of segmented driver. Segmented means we don't use a single driver, like we have we take a unit, we put them in parallel. They're like legs, they're like segmented. Okay, so segmented driver, okay, many things in parallel, right? And this architecture, as we know, right, UCIe meant single-ended signaling. Okay, so the one which is widely used is this SST, source series terminated the driver, or from the IO angle we say it's a stub series termination logic. Okay, so you can clearly see the meaning of here, right? What is this? This is a pad, right? And assume it is the source of it, and we have a series resistance. Assume after this pad is some some Z0, inter chiplet package, the root, right, interconnect, right? So and I need this from here to that path, we need to have a continuous impedance continuity. Okay, so we will have a additional, you know, the impedance in this path, series to the source. Okay, so what is the optimizations here we can do additionally? What UCIe talks about is separate pull-up and pull-down strengths for various channel configurations. Maybe we sometimes we do off-chip, you know, terminations, on-chip terminations, you know, at different speeds, you know, so many things like in upper, right? Okay, separate pull-up and pull-down strengths. So it means they're programmable, as simple as that. And impedance control loop, okay, to compensate the variations. For example, here you see the RS, right? It is like variable now. I can set it to 118 ohms, I can set it to 50 ohms, I can set it to, you know, as per the requirement at system level, right? Impedance control loop. These are the optimizations, you know, they talk about. And the low power states, you know, the transmitter driver, you know, it needs to be a tri-state, you know, capability for power saving. For example, I'm taking an example of a tri-state inverter. You can just imagine that. So, you know, at some time when enable is, you know, implemented, Y is at Z, you know, high impedance. So similar, same thing can be applied, concept can be applied for the driver also. Okay, and EST and high data rates, that's also a very important part of it, because see, minimize the pad capacitance for EST production, because you know, you need a EST production. We saw that CDM production of 30 volts is mentioned in you know, the UCIe spec, right? So the moment you add a EST production, it adds a load to it, a capacity load, right? So then how do you do it? You know, it limits the speed. Okay, so minimize pad capacitance, that's one thing. How do you do minimize capacitance? How do you minimize the capacitance? Yeah, okay, think. And these are the pad capacitances mentioned, you know, for advanced package as well as yeah, for advanced package, right? So here you see transmitter speed. So it mentions 250 femtofarad for all the speeds. For example, if you are talking about 32, 125 is the, you know, femtofarad. Okay, this is for driver side of it. Okay, transmitter side of it. Whereas receiver side, if you can see that 200 femtofarad at pad side, remember. So for say 32 gigatransfers per second, we have 125, you know, femtofarad, the pad side of it. Okay, so because, and we are able to see achieve such a low capacitance of the package because the packaging technology is very advanced now. Okay, see, we used to use, you know, sometimes 5 pico for packaging, sometimes 30-40 older technology, older nodes we used to use 35-40 picofarad at pad, you know, capacitance of the pad, you know, and we imagine, you can't even imagine, you know, achieving such a giga, you know, data source per second with that big load, right? That's okay. And because we are transmitting data at very high data rates, and inductive peaking techniques, for example T-Kyle example, might be required for higher data rates. Now how is that? We can, some of the examples are given here. For example, inductive peaking. Okay, so this is a T-Kyle kind of an architecture. These are also a T-Kyle kind of an architecture, you know. This is also a T-Kyle, you know. Okay, so basically, you know, use the technique of inductive peaking and to increase the bandwidth or increase the data rate. CDM also, as I mentioned, you know, it's 30-volt CDM. Okay, and we are anticipating it. This expected protection level going down to 5 or 10 volts, and that will further, it helps us to increase the speed of data rate. Now, you know, we learned the transmitter, the circuit part of it, right? Now let's see, you know, electrical parameters of it. Okay. Some of these are listed here. For example, data lane transmitter swing. The minimum it's given is 400 millivolts. Okay, and think above is good. Okay, so it's a voltage range of the data signal on the transmission line. You know, swing. Okay, because remember it's a, you know, there's a single-ended, you know, signaling it is. So similarly, same thing applies for you know, for our clock transmitter swing also. Okay, it's also single-ended. Okay, so 400 millivolts is the minimum one. Okay, how do you measure? I mean, third one is incoming clock rise. clock rise or fall time. How it is measured? It's measured from 20 to 80% here, right? Time it takes for the clock signal to transition from, say, logic high to logic low, okay, or in between them, right? So again, it's measured in terms of the unit intervals. Okay, so next one is the incoming differential clock overlap. For example, generally what we assume, especially if it really matters in because we talk about high speed, right? CML circuits or flip-flops, CML based, the clock dividers or flip-flops or master slave flip-flop, you can imagine it, right? So we ignore the when signals are simultaneously switching. It means these are differential signals, right? At some time both transistors will be on. There's overlap in between. One thing, other thing is that a slew also. For example, you have this positive signal coming here, clock, and here this can be a overlap. Second thing is, for example, this is one, right? This is, I'm supposed to come here, but it comes here little bit delay. So there is a for some momentary both are on. Okay, so simultaneous overlap, or it can be both are off at a time, right? In this time your flaps can be transparent also, or some Q node can be floating also. It could lead to some of the other malfunctions, right? So what is the allowed thing? So allowed overlap between rising and falling edges. Rising edges, falling edges, supposed to go here, or allowed overlap. Okay. Also differential signal. And driver pull up and pull down impedance, generally, yeah, the strength of the internal circuits that pull the signal up or down at a specific level. For sometimes generally we have a pad, okay, and but sometimes we need weak pull up to some voltage, some VDD like that, right? To a specific voltage level. So how it is measured is a specific voltage level. Driver pull up pull down impedance is calibrated at a midpoint of the transmit voltage, because how do you do that? There is a signal swing is right here like this, single ended anyway, sorry. Here, right, the signaling like this is a midpoint here, and it's captured. Okay, impedance is captured. Okay, the impedance step size, sometimes we the source impedance, right? You're talking about pull up and pull down impedance. What is the, sometimes it's programmable. What is the granularity of adjustments we can do that. And 1 unit of total jitter, the jitter definition, right? So similarly the other kind of jitters, deterministic jitter. Okay, so on data clock differential jitter. Okay, duty cycle error. For example, we wanted to a 50% duty cycle, how much is deviated from the ideal. And a lane to lane skew correction range, okay, adjustable range to compensate that for timing differences between the different data lanes, because we need a symmetry across, right? And lane to lane skew also, okay, uncorrected timing difference between the data lanes. Okay, so these are some of the things. And the clock to mean data training accuracy, how well the clock signal is aligned with the average data signal, that's important, right? And phase adjustment step, the granularity of adjusting the phase of the clock signal, because sometimes we adjust the phase of the clock, the clock, right? And effective pad, these are some of them are effective pad capacitance in the advanced package. These are some of the electrical parameters we UCIe talks about your transmitter. Let's look into the equalization part also in the transmitter side. So why it is required? Why it is important is it combats the inter-symbol interference, which is common in high data rates, right? You can get some idea what exactly it is, how it is the ISI corrupts your actual signals, right? So your present voltage level, it's not independent. It also depends on previous, the voltage level at that particular pad, say for example, right? So if you look at this example, and I'm supposed to get 1011 here, like 101, I don't know what is happening here, right? This is good here because all of them are 10. We have got enough time to discharge here. Okay, but now we went to 0 and suddenly charge going to the 1, and capacitor check sometimes to charge, right? So come back to that, right? So look at it here, and I don't know whether it is 0 or not. And ISI, Okay, right. Coming back, requirement, right? So what is the requirement? You know, the UCIe specification recommends, you know, the equalization of for 16 giga transfers per second, you know, the speed data rate, whereas it mandates the equalization for 24 and 32 giga transfers per second data rates. And what is the technique? Definitely transmitter de-emphasis. You know, it reduces high frequency components of the signal. Okay, so some of the coefficient selections I mentioned here, let me not go there in detail, but otherwise the configuration, right, you know, the transmitter, you know, needs to support the predefined settings not given here, and see here, this is a 1 voltage level, this is a 1 voltage level, you know, think of this, you know, transmitter, it's a transmitter output. Oh, de-emphasis waveform transmitter, right? So optimizing settings chosen based on the initial configuration or training sequence. Of course, you prefer a large eye opening. Maybe we need to deal in detail in some other slides. We have some more to go. Receiver, it may take time. Let's close it here. Okay, thank you for your interest.